So good morning to all. Let us start our second class. So in last class we have taken a set of class functions or certain class of functions y of x, and we have associated by certain law that is j equal to j of y of x, and we have associated that functions by an integral that is a to b f of x y dash dx. Okay, and where we have restricted the interval up to a to b, and we are considering the end point also. Since we are extremizing the function within a certain interval, so we need a boundary conditions, and we cannot find the extremization of that function with the help of initial conditions, because initial conditions act only the neighborhood of a certain points. Okay, so it's compulsory to need a boundary conditions for extremizing a function, and if there is no boundary conditions present in the variational problem, then we can only find out a general extremal, that is neither maximum nor minimum. Okay, so to extremize a function in a functional, we have derived a equation, that is Euler equation, which can be easily used for finding a extremal of a variational problem. So that we have not to derive all the things directly. We can use this Euler equation to find the extremal of the problems. So this is the Euler equation, and here we have considered only one dependent variable and the derivative of first order of dependent variable. Okay, so f of x y dash dx, and for that we have derived this Euler equation, which gives you the extremals of a function in a variational problem. So for simplification purpose, what we have done, we have derived a similar formula from equation 3 to see the Euler equation when f is independent of x and when f is independent of y. So that here we find second equation. Yeah, this also I have already discussed in last class. This one. This is the second equation that we have derived from the Euler equation. That is 1 by y dash dy dx f minus del f by del y dash into y dash minus del f by del x equal to 0. So in which we can see if f is independent of x, then we can set up the Euler equation, that is f minus del f by del y dash into y dash equal to c. And if f is independent of y, then we can set up the Euler equation from equation 3. Okay. So one is del f by del y dash equal to c if f is independent of y, and if f is independent of x, then you can say the Euler equation becomes f minus del f by del y dash into y dash. Okay. So up to this we have discussed in the last class. Suppose we are taking an example here. 0 to 1 y dash cube dx. The conditions are y of 0 equal to 0 and y of 1 equal to 1. So it's a boundary conditions, and it's the variational problem where the function f is y into y dash cube. So first we try to see is f is independent of x or independent of y. If f is independent of x or y, then directly we can use this equation 6 or equation 7 for finding the extremal of the functions or variational problems. So here you can see easily that f equal to y dash cube. So f is independent of x. So directly we can use here equation 7 for finding the extremals. Okay, so the Euler equation being f minus del f by del y dash into y dash equal to constant. Okay, so since f equal to this one, so you can write this one f del f by del y dash, that we can write here 3y dash square, and since there is a multiplication of y dash here, so we can write 3y dash cube. Okay, so here we can write y dash cube minus 3y dash cube, that's equal to 2 minus 2y dash cube, and upon simplification we can write here y dash cube equal to minus c by 2, that's equal to constant key. Okay, so this is the Euler equation, or this is the simplified Euler equation from this variational problem when f is independent of x. Okay, Now we try to solve this differential equation. Now you can see it's a simple differential equation of first order. Y into y dash cube, that's equal to k. That means we can write y into, this is dy by dx whole cube, that's equal to k. Okay. If you want to find out the integration on both sides, you can easily solve this differential equation. So we can write after simplification, this becomes y to the power 1 by 3 dy, that's equal to k 1 by 3 dx. What I have done here, since this is dy by dx whole cube, so we have taken the power as 1 by 3 on both sides. So this becomes y dash only, and this y to the power 1 by 3, and this k to the power 1 by 3. Okay, since this y dash is of now degree 1, so we can write dy by dx, y to the power 1 by 3 into dy by dx, that's equal to k to the power 1 by 3. Or upon variable separable, we can write y to the power 1 by 3 dy equal to k to the power 1 by 3 dx. Now upon finding the integration, we can write on the left hand side, that's equal to y to the power 4 by 3. And on the right hand side, we can write this one as 4 by 3 k to the power 1 by 3 x plus c1. Okay. Since there is a presence of conditions here, y of 0 equal to 0 and y of 1 equal to 1, we can find out the extremals, either maxima or minima of this variational problem. So upon using this y of 0 equal to 0 and y of 1 equal to 1, here, since there are two conditions, and in equation also, there are two number of constants associated with the general solution. One is k, another is c1. Okay. Upon using these conditions, y of 0 equal to 0 and y of 1 equal to 1, you can easily found the solution called the y to the power y equal to x to the power 3 by 4. So this is the extremal for this variational problem. Okay. And graphical illustration, I will show you. In graphical illustration, we can see that extremal, either it may be a maxima or minima. I will show you. Next, we go for another example. Suppose you are taking this type of example. J equal to a to b root over of 1 plus y square by x into dx. If you try to find out there are no conditions present in this example. Now, if you try to find out the extremal of this variational problem directly by using Euler equation 3, so you may face some problem here. So first we'll check here, is the function f is independent of x or y? If either independent of x or y, then you can use this formula 6 or 7 here. Okay, so that we can get the Euler equation so easily, or the associated differential equation so easily. So here you can see this is the value of f, and this function f be independent of y. So we can directly use this equation 6 as the Euler equation. Okay, no need to use equation 3 as the Euler equation. So since f is independent of y or f does not involve y, we can write the Euler equation del f by del y dash equal to c. That means if we find the differentiation with respect to y dash, we can write this one like this: y dash divided x into root over 1 plus y dash square, that's equal to 1 by c. Okay, so simple, it's a simple differential equation of first order. So upon finding the integration on both sides, we can write this one as dy equal to x dx divides root over c square minus x square. That means you can easily find out this differential equation. Okay, so dy equal to this one. So here we can use the variable transformation for finding the integration of this differential equation. So if we take x equal to c sin theta, we can write dy equal to c sin theta d theta. So upon using this one here, so it becomes so simple, so that it will give you the solution as y equal to minus c cos theta plus b. Okay, and upon simplification, we can write, upon simplification means upon elimination of this theta, we can write this equation as this one. So x square plus y minus beta whole square, that's equal to c square. This is the equation of circle. Okay, so this is the extremal of this equation. Okay, so now if we proceed further, In last functional, we have taken y up to first derivative. If you extend further here, suppose we are taking second derivative in the variational problem. That means y double dash. Now our function becomes function of x, y, y dash, and y double dash. Since we have introduced the second derivative in the function. Now here also we can follow the same procedure as we have used for finding the Euler equation for a function which contains x, y, and y dash. Okay. So if you follow that procedure, you can find the Euler equation like this here also. Okay. So no need to derive all the process one by one. So we can use the similar process for writing the Euler equation here. So for y double dash, here we can write the Euler equation like this: del f by del y minus d by dx del f by del y dash plus d2 by dx square del f by del y double dash. Okay. Now this is the Euler equation that can be used to find the extremal for a variational problem which contains derivative up to second order. If we write an example like this, find the extremal of the functional 0 to 1, 1 plus y double dash square dx. Okay. So since here the order of the derivative be 2, but the degree of the highest order derivative present in the function, that's 2. So we need 4 number of conditions for finding the extremal of the function. Okay. Otherwise, you can think here, since this is Euler equation, if we think here, the third term d2 by dx square del f by del y double dash, this del f by del y double dash, it will give you a function, whatever the function, it contains a second order derivative, that is y double dash here. Okay. If we write here d2 by dx square of y double dash, so it becomes fourth order. So we need 4 number of conditions for finding the solution of this differential equation. So while we are considering a function that contains derivatives up to second order to find the extremal of that functional problem, in that case we need 4 number of conditions. In the previous case, we have taken the derivative up to first order. So in that case, we need only 2 number of conditions for finding the extremal of the functional. Okay. Now, if we extend further, suppose this y be extended up to third order, y triple dash. Okay, so in that case, we need 6 number of conditions for finding the solution, for finding the extremal of the functional or extremal of the variational problem. So here, since we have taken up to y double dash, so we need 4 number of conditions that can, and this is the function associated with the extremal, sorry, functional. So the function will be f equal to 1 plus y double dash square. And the conditions are y of 0 equal to 0, y dash 0 equal to 1. So we have taken 2 conditions at one point, another 2 conditions at the other endpoints. Okay. In a similar way, if someone consider up to y triple dash, so we need 3 conditions at initial point and 3 conditions at final points, and so on. Means if you're taking up to nth order, in the same way, we need n number of conditions at initial points as well as n number of conditions at the boundary points. So since here f equal to 1 plus y double dash square, so these are the conditions. Now, if we use Euler equation here, the Euler equation be del f by del y minus d by dx del f by del y dash plus d2 by dx square del f by del y double dash, that's equal to 0. If we find del f by del y, here we cannot use that f is independent of x or independent of y. If someone try to use that one, you have to simplify this Euler equation further. Okay, so no need to use that one here. And that independent of x or independent of y, that can be used for a function which contains derivative up to first order only. Okay, so we are not thinking about function independent of x or independent of y here. Directly we can use this Euler equation here. So if you find del f by del y, that becomes 0. Del f by del y dash, that's also becomes 0. So we only consider del f by del y double dash. Del f by del y double dash, that's equal to 2 into y double dash. d2 by dx square of 2 into y double dash, that gives 4th order derivative. d4y divides dx4, that's equal to 0. Okay, so it's a 4th order differential equation. If we find the solution of this 4th order differential equation, it becomes y equal to a plus, either you can write c1 plus c2x plus c3x square plus c4x cube, or a plus bx plus cx square plus bx cube. That means there is a need of four number of constant in writing the general solution of this fourth order differential equation. Since it contains four number of associated or arbitrary constants, and we have four number of conditions here to finding the constant associated with the general solution. So we can use this condition for finding the constants. Okay. So upon using the boundary conditions, you can use so easily. Suppose I am using first y of 0 equal to 0 in this equation. So what it gives, this left hand side with 0. Since x equal to 0 and y equal to 0, yeah, this 0, this a, b into 0, 0, c into 0, 0, d into 0, 0. So we'll get a equal to 0 by using the conditions y of 0 equal to 0. Okay, now a becomes 0. The remaining solution be y equal to bx plus cx square plus dx cube. Okay, next we have to find out, suppose we are using y of 1 equal to 1 also. If we write y of 1 equal to 1, we can write here, this is 1, this b plus c plus d. So one equation, that is b plus c plus d, that's equal to 1. Okay, and thirdly, we can use this one, y dash 0 equal to 1. If we find y dash here, this becomes b, this becomes 2cx, this becomes 3dx square. And if we substitute x equal to 0 here, so these two terms that become 0, so we can get b equal to 1 here. Okay, and another equation we've already got, b plus c plus d, that's equal to 1. And if we substitute y dash 1 equal to 1, you can get another equation. By solving these two equations for x equal to 1, you can get the other values of c and d. That means finally you can get a equal to c equal to d all are 0, and b equal to 1, that we got from y dash 0 equal to 1. So hence the final solution or final extremal is y equal to x, and this is a unique solution for unique extremal, and the extremal be y equal to x. And suppose we are taking this example. Find the extremal of 0 to pi by 2 y double dash square minus y square plus x square into dx. Okay, since here the derivative is up to second order, there is a need of four number of conditions here. So the four conditions are like this, and here the interval be 0 to pi by 2. So we have set up two conditions at the initial point, x equal to 0. Another two conditions we have set up at the end point, x equal to pi by 2. So these are the conditions. Now you have to find out the extremal. So we have to set up the Euler equation first. So the Euler equation becomes y of ib minus y equal to 0. That means d4y divides dx4 minus y equal to 0. Okay, it's also a simple differential equation of fourth order. So you can easily write the general solution. So general solution be y equal to a e raised x plus b e raised minus x plus c cos x plus d sin x. Okay, now here also we can use this condition to get a unique extremal. So if you use the boundary conditions, we can get here a equal to b equal to d, that's equal to 0, and c equal to 1. So here we can get the extremal is y equal to cos x. That's a unique extremal for the functional this 0 to pi by 2 y double s square minus y square plus x square into dx. Okay. If we take another example here, suppose the interval be minus 1 to 1, and the function be y double dash square plus y, that's into dx. Okay, so here also we have taken two conditions at x equal to -1, another two conditions at x equal to 1. So the conditions are y of plus or minus 1 equal to 0 and y dash plus or minus 1 equal to 0. That we have set up the conditions. If you find the Euler equation here, you can find, I think there is a mistake here. No, it's okay. If you find the Euler equation del f by del y, that's 1. Del f by del y dash 0. Del f by del y double dash, that's equal to 2y double dash. So when we find the d2 by dx square of this 2y double dash, it becomes 2 into d4y divides dx4. This one. This plus 1, that's equal to 0. I think this becomes half after some time. So yiv equal to minus half. Okay. So upon finding the solution of this differential equation, you can get y equal to minus x to the 4 by 24. It comes from the particular solution of this differential equation because there is a presence of f of x here. Okay. And this a plus bx plus cx square plus dx cube, that comes from the complementary functions yiv equal to 0. So this is the general solution in which there is a association of particular solution as well as a complementary function. Okay. Now, upon using the boundary condition, this y plus or minus 1 equal to 0 and y dash plus or minus 1 equal to 0, we can get the general solution, this one. Y equal to minus 1 by 24, x square minus 1 whole square. Okay. Now, if we proceed further, if f involves y triple dash, then it becomes, the Euler equation becomes like this. That means we have just extended here this term by giving minus t3 divides dx cube del f by del y triple dash and so on. Now, question is that if we take an yn here, so we can write the last term as dn by dxn del f by del yn, and if you see the sign associated in the Euler equation, these are of opposite sign. So first one, negative, positive, negative, positive, and so on. So where there is a presence of even order, the sign be positive, and when there is a presence of odd order, the sign be negative. Okay. So in the same way, we can set up a Euler equation of function which contains derivative up to nth order. So next we will discuss if the functional contains more dependent variable. So here x be your independent variable and y be dependent variable and y dash be dependent variable. Suppose we are extending here the dependent variable here. So in the first problem we have taken f of x, y, y dash. After that we have extended the derivatives. Okay. And the general extremal problem, that is of the form of f of x, y, y dash up to yn. That's the general form. Okay. First we have started from order 1 and then we have extended up to order n. So this is the general extremal problem. Now question is that if we extend the number of dependent variables that is associated with the extremal problems. So the dependent variable will be y. Now what we have done here, we have extended the dependent variable. Suppose there is a presence of n number of dependent variables, that is y1, y2 up to yn. So in such a way, we can write the derivative also, that is y1 dash, y2 dash up to yn dash. So this is the extremal problem, functional problem, or we can say variational problem that contains more than one dependent variable and the derivative is up to first order. So in that case, so what happens to the Euler equation here? For one dependent variable, you can get one Euler equation. Okay. Since here n number of dependent variable, we can get here n number of Euler equation. So in combined form, you can say it gives you a system of Euler equation. So here we can say the relevant Euler equation are n simultaneous equation. For one dependent variable, it will give you one Euler equation. Since here n dependent variable, it will give you n number of Euler equation which are mutually interconnected with each other. So for I equal to 1, we can write del f by del yn minus d by dx del f by del y1 dash equal to 0. And for I equal to 2 also, we can write, and in a similar way, we can say it defines a system of equations, or you can say system of differential equations, which is of first order. Suppose we are taking an example here. Find the extremal of the functional 0 to pi by 2 y dash square plus z dash square plus 2yz dx. So now here the question is how to determine the conditions. The number of conditions depend upon the order of the derivative as well as the number of dependent variables. Okay, since the order of derivative be 1 for y and 1 for z, so we need two number of conditions for y as well as two number of conditions for z. So in all, it requires four number of conditions if we are taking a variational problem where the function is function contains two number of dependent variable and f is of the form of x, y, z, y dash and z dash. Okay, so here our f is this one y dash square plus z dash square plus 2yz. So condition for y, that is y of 0 equal to 0 and z of 0 equal to 0. Similarly, we can define the condition for condition for y of 0 equal to 0 and y of pi by 2 equal to 1. And the condition for z is z of 0 equal to 0 and z of pi by 2 equal to minus 1. Okay. In both cases or both variables, we have defined the conditions at the endpoints. One at x equal to 0, another at x equal to pi by 2. Okay. So for the dependent variable y, we can get one Euler equation, that is y double dash minus z equal to 0, and second one that gives you z double dash minus y equal to 0. You can see from here also. If I find del f by del y minus d by dx, del f by del z dash, del f by del y minus d by dx, this is del f by del y dash. So here if we write here del f by del y, that is 2z, and minus d by dx, del f by del y dash, that is 2y dash. And when we are finding the differentiation of 2y dash, that becomes 2y double dash. So in simplification, it gives this form y double dash minus z equal to 0. And similar, second del f by del z minus d by dx, del f by del z dash, that's equal to 0. It gives you z double dash minus y equal to 0. Now you can see it's a system of differential equations. Okay. So you know how to solve system of differential equation. So in this case, since these two equations are quietly independent, so we can find the solution one by one also. First, we can find the solution. No, they are dependent. So we can use one equation upon the other for finding the solutions. Okay, so we can say that is a substitution method. So here we can write y equal to z to the power or d2z divided dx square. If we introduce this y in equation 1, now this equations becomes a differential equation of fourth order, which contains only the variable z. Okay, so it becomes d4z divided dx4 minus z, that's equal to 0. And upon solving this fourth order differential equation, which is of homogeneous type, directly you can get the solution like this: a e raised x plus b e raised minus x minus c cos x minus d sin x. Okay. Now, if we use this value of z here, you can get the value of y. That means you have to find out the second derivative of this z. Okay. Here, what I have done, I have first calculated the value of y. After that, I have calculated the value of z. You can do either way. Okay. So this is the value of y and this is the value of z. Now, here there are two number of solutions present for this variational problem. One is y of x and another is z of x. And the number of constant associated with the solutions, these are four. One is a, b, c, and t. Since there are four number of conditions present in the extremal problems, so we can use these four conditions for finding the constants. So upon using the boundary conditions, you can find the constants as a equal to b equal to c equal to 0, and you can get the value of d as 1. Okay. If we substitute this t equal to 1 in equation in y of x as well as z of x, we can write the value of y as, that is sin x, and the value of z as, that is also sin x, because we are taking d equal to 1. So these are the extremals of this variational problem. 0 to pi by 2 y d square plus z d square plus 2yz dx. Similarly, if we take another example here, that is, suppose y d square plus z square plus z d cube of dx. Here also we need 4 number of conditions, but we see what about the Euler equation here. Now the Euler equation like this. So in the previous case, you can see these Euler equations are dependent upon each other. That means one can be substituted in the other equation to find the solution of the Euler equation. But here you can see either you can get like this also. That means your Euler equation may be quite independent. That means this first Euler equation doesn't depend upon the second Euler equations. Okay. So here, first equation that gives the solution is this one, y equals c1x plus c2, because it's the second order differential equation. And if we try to solve the second one, it's only means it is also a homogeneous type of differential equation that gives you the solution, this one, z equal to c3 e to the power x plus c4 e to the power minus x. Okay. Now, upon using the conditions, here we can get the solution. The constants are c1 equal to 1, c2 equal to 0, c3 equal to this one, and c4 equal to this one. And the general solution is y equal to x and z equal to sine hyperbolic of x minus 1 divided sine hyperbolic of 1. That means upon substituting this 1 by e square minus 1 and e square by e square minus 1, and after some simplification, either you can write the solution in e form or otherwise in hyperbolic form. Okay. So this is all for the today class. I'll send you the materials today, and in next class we'll study the geometrical significance of these extremal problems. So how we'll determine the maxima or minima for a variational problems geometrically, or geometrically what it show in a I think we can say geometrically what it show in a variational problems, or what means what does it mean maxima or minima, and what is our objective in finding the maximum minima, that we'll discuss in the geometrical significance of these extremal problems. Okay. Now, if you have any query, now we can ask. And today I will send you this both lectures note, that lecture note 1 and lecture note 2. Okay, I will upload in Google Classroom. Any question? If no question, then we'll meet in next class, and I'll send you the lecture note today. Okay.